And this actuator is connected with the deployment system. As I told you, the deployment system, whole spacecraft is bundled together and slowly it expands in the vacuum and low G environment. If you deploy them earlier, perhaps it will break down because of pressure and gravitational force. And things are designed for a certain environment, and there only it has to be deployed. I told you about the cameras. There are different types of cameras that are being used in spacecraft, very small to very large camera. The largest camera being used in spacecraft, Galileo, is a space telescope which has revealed unknown planets at thousands of light years away, which we couldn't see through the Earth telescopes. So, to find out the aspect or the position of the spacecraft or satellite, we need gyroscopes which can find out, take the absolute position or orientation, not position, orientation of the satellite using gyroscopes. Then comes the power. There are various payloads and electronics which needs different voltages, and different voltages should be isolated to each other.
Yes, sir.
So we need DC to DC. A general DC bus runs around, and from this DC bus, small DC to DC converters are used for various experiments.
Yes, sir.
And this serves two purposes. One is they isolate one experiment from the other. Any short circuit or failure in one electronics gets limited to that particular DC-DC converter, and other system doesn't get affected by such things. And then this again isolates the experiment from the rest of the grounding system and power system.
Power systems.
And this DC-DC converter obviously goes through regulated power supplies. Each of them are connected with regulated power supply, which generates desired voltage. And whenever we talk of regulator, there is a power loss, and we cannot withstand power loss. We don't want to waste this expensive source of power there. So for that, switching regulators are used.
Okay.
But the point again, when you use switching regulator, they generate noise, switching noise.
તો પછી કરીએ શું?
And sensitive, जो sensitive sensors હોય, that will get disturbed. So for them, we compromise, and those portions we use linear regulators.
Yes.
So
Yes, sir.
we specially use linear regulators.
regulators.
Although it loses some power, but those sensors take less current, so we can afford to have a linear regulators there. And I believe most of you are familiar with regulators. Then the to analyze and process on board, and processing on board is required because when you process huge amount of data compression takes place automatically. And this data compression helps us two way. One is less data is to be transmitted. Secondly, a validation of the data takes place on board itself
Yes, sir.
while analyzing. So this affects, this helps, and these are done with VLSI devices like embedded systems, and nowadays more and more FPGA, field programmable gate array, very large scale integrated circuits and field programmable gate arrays are being used. Chandrayaan 2 and Chandrayaan 1. Chandrayaan 2 especially is using many gate arrays to analyze spectral ranges of energy. Sensors are being connected with AD converter, which digitizes it, and most of the actuators or output devices are connected to D to A converter, which converts analog digital to analog voltages. And last but not the least, we need a lot of amplifiers
And oscillators.
and oscillators. Some of the sensors which are, you are asking, what are Chandrayaan?
Yes, sir.
So these are some of the detectors. One of the detector was SI pin diode. Now, what was happening in Chandrayaan? We were taking photograph, or we were collecting the data by illuminating moon surface using X-ray.
Yeah.
And where this X-ray came from? This X-ray came from sun. Like sun illuminates optically, sun also illuminates planet surfaces through X-ray.
Yeah.
And because moon doesn't have any ionosphere, the X-ray penetrates to the, Now we want to measure how much X-ray at a given time, because sun's X-ray changes from time to time. Solar flare, it increases,
Yes,
solar activity. So we want to measure both how much sun is radiating and how much moon is re-radiating.
Re-radiate.
So these are the two equipments on board space shuttle were used. Silicon pin diode, which was looking at sun all the time.
Yes.
They were opposite looking. And cadmium zinc telluride. I'm lucky I was one of the designer. I was in Chandrayaan-1 designing cadmium zinc telluride detector for X-ray two-dimensional imaging. And then other X-ray CCD detectors are also available. They are also being used for fluorescent studies.
Okay.
And we'll see some of the photographs as we go along. Now, CZT, cadmium zinc telluride, the lab experiment looks like this. This is the sensor, cadmium zinc telluride. It has a interface electronics. You analyze and view the data in PC and the power supply system.
Yeah.
These are the live, actual modules. You were asking what is space electronics. These are space electronics.
Okay.
This is what goes in actual
Instrumental
satellite.
Yeah.
And if you see them, they're collimators. This, because for X-ray the lens will not work for collimation, neither any reflector. What we use piston case type of setup, which allows parallel beam at a given angle only it can enter, rest of them will get absorbed by the walls. So this is a collimator. For the device there were 16 sensors in one of the experiment, and there are anti-coincidence, because these pulses, the radiation counts which are coming, some of them could be false.
Yeah.
To avoid false count, we use anti-coincidence. So
तो सर इसका मतलब ये हुआ कि अगर जो हमारे काम की चीज़ नहीं है वो यहाँ से रिफ्लेक्ट होके वापस चली जाएगी.
yeah, we will find out the coherence of two pulses. You can say any random thing will not be coherent.
Yeah.
And whenever a genuine signal burst comes, it will come both the places. So we can identify by this,
Okay.
like a truth is always coherent.
Yeah.
Any person talking will be same,
हाँ.
whereas a false, a lie
There
will
is
not be
variety.
same.
Yeah.
So noise will not be same in both
Yes, sir.
cases. So
तो
this
ऑटोमेटिकली
could be
यहाँ
analysis.
पे डिटेक्शन ऑटो डिटेक्शन होगा
Yes,
ताकि पता चले कि ये इन्फॉर्मेशन ये सही है ये गलत है.
absolutely.
ओके.
So you can see different experiments here.
ये सर एब्जॉर्ब जो करेगा रेडिएशन दैट इज डिफरेंट थ्रू
Yeah, different
कॉलिमेटर्स
experiments.
ओनली.
The different sensors are shown here. Hex, as I told you, high energy X-ray data
These are the
interface
varieties of
packages.
sensors only.
Yeah, these are
Okay,
the
sir.
electronics and sensors.
Okay.
The sensors which did actual measurements.
Yes.
Now, this is a picture perhaps long back we had taken when we have started Chandrayaan-1, you wanted to
Arey
know.
wah.
And the gentleman here is Professor Bhandari. He is the person who had proposed Chandrayaan-1 or mission to moon from PRL. And these are the Planetary Exploration Lab. And here CZT is being tested the first time. Cadmium zinc telluride here. Some of the other electronics we thought we'll show you. These are from different places, even universities. This is, as you can see, the nano satellite propulsion system. Cameras, high resolution, high quality imaging cameras. Now, when we send a mission, important thing is it has to go to the right orbit
Yes, sir.
and at right time. And these computations are very important. Let's look at, and I suggest all of you, if you have enough time to note it down, these are very simple equations which are heart of most of the space travels.
Yes,
the
sir.
way we send transmit. I will show you how these are different. We don't use differential equation for computer simulation or actual control. We use difference equation. If you look at it, is very simple. If you see the motion equation, I don't have to remind you. This is Newtonian equation. Okay, for distance,
Yes, sir.
velocity,
यस सर.
force.
और सर ये हमारा जो ये चंद्रयान-2 है, ऑब्वियसली इट इज़ अ पोलर सैटेलाइट. इट्स अ पोलर, नॉट
For
इक्वेटोरियल.
Earth,
फॉर अर्थ.
for Earth, when it comes out of Earth, it is a polar orbiting satellite.
Okay.
And then once it goes out, then the
It
way
will become
we
a-
will show you how
Okay.
it goes.
नहीं, ये जो लाइन्स है
हाँ,
ना, तो हो
हाँ.
सकता है हमारे स्टूडेंट जानने की
both are,
कोशिश
both are.
करेंगे.
I will show you that.
Okay, sir.
I will show you the live. But let's look at this equation quickly. The center of Earth, if we consider x0, y0, and xic is the position of the body,
Yes,
which
sir.
is rotating
जहाँ पे-
around, and velocity at any point is vx, yx, and the distance could be given by center minus position. So x square
X.
plus y square is equal to r square, we know. Square root of that is a distance.
Yes,
so
sir.
this up to this is fairly simple.
यस सर.
Now, any change in delta t, how the velocity changes, if you look at this, xc minus 1 xc d cube,
By
it
d
is
cube.
again vx, velocity in x direction, because we have to split it in two components.
Yeah.
Vertical, which is dragged by gravitational force, and horizontal, which is centrifugal force.
Yeah.
So both the velocities are calculated, and then rest of it is very simple. This is iteratively added to the actual velocity, and actual velocity when in two component. If you go on plotting them, you will find the trajectory what is being done
Like
here.
this. Okay,
Right,
sir.
right. Now the destination moon. We'll show you how to go to moon, but moon has attracted young hearts
Yes, sir.
from ages.
Yes, sir.
And many young guys have promised their better half to bring
In the
a
presence
portion of the moon,
only.
bring a portion of the moon.
Yes,
And not many could do it except Neil Armstrong and few
Yes, sir.
few others who could really bring the moon, and we'll see how to reach. Now in the scientific world we can plan how to reach to the moon.
Yes, sir. That is the most.
That is the method of reaching to the moon. Just
Yes.
promise is not enough. You should know how to reach to
Yes.
the moon. So apparently many people have done many research based on the resources, time optimization, price optimization, how to reach to the moon. A typical method of reaching to the moon is generate an elliptical orbit, and it should be so elliptic that it gets to the moon's orbit.
Okay.
That's the first slide you can see. First it starts with a parking orbit, here, and then thrust is given. Retro rockets are fired at this point.
Sir, excuse me. What is parking orbit?
Okay, there is invisible orbit, you can say, and as you know, once it is in orbit, it doesn't need any energy to stay there. Like you park a car,
Okay. Okay.
so we park a vehicle, spacecraft there,
Okay.
but it is not steady.
Permanent
It is
place.
going
Okay.
round and round.
Okay. Okay.
In a stable orbit. So we call it a parking orbit.
Yes, sir.
It's a place in between home, and from this parking orbit, once we give accelerator, we kick on accelerator, it generates different types of orbits at different direction, and that could be precisely computed. So this is one of the way to, and this is expensive because a large amount of energy is required.
Yes.
Here, this is a Japanese model, and this is a very interesting model. They say that this is where the moon's orbit is. Here it is much condensed. Moon's
Okay.
orbit here.
Yes, sir.
And you go much away from moon. By escape velocity, you get out of the Earth's gravity, even moon's orbit, and then when it comes back with very low energy, you manipulate and maneuver so that it gets into moon's orbit.
Moon orbit.
But it takes long time, as you can see here. It takes long time compared to this. Most appropriate and low energy, the one which Chandrayaan-1 used, is this type of orbit.
Yeah.
Whereas you start with the parking orbit, go on increasing it, then once you go to sufficiently elliptic, then give a kick to get out of Earth's gravitational field and go and park around moon's orbit.
Okay.
And you do it in two phases. First you go to 1,000 kilometer, that's what it was planned, a 1,000 kilometer parking orbit. Once you are stable, you have seen things around, your instruments are good, then you come down so that you can take more accurate observation of moon surface.
Yes, sir.
And that is 100 kilometer height. We had planned 100 kilometer height, but end up finally, because of certain environmental problem, 200 kilometer we gone round Earth. Let's see. I have a small simulation. That's what we are asking, how those equations
Yes,
are
sir.
really used. This, you see, 2002 we had simulated much before Chandrayaan-1.
Yes, sir.
The satellite going round,
Yes, yes.
and now it is going out of the orbit of, this time gone, kicked.
To the
This is not to the scale, but then you can get an idea how things happen. Now it is on a
Yes.
larger 1,000 kilometer parking orbit. It is going round moon,
Wow, how nice.
and once it goes around in a polar orbit, the way you are seeing moon moving, it is moving in 30 days once,
Okay.
because it is always looking at Earth, and around Earth it goes in 1 month approximately.
Yes, sir.
So it revolves. Now once the satellite revolves around, it almost scans every portion of the moon surface.
Yes.
Okay, this distance was expected 100 kilometer. We had given it final shape of 200 kilometer.
હાઉ નહીં સર, બહુ સરસ છે. આઈ એમ શ્યોર સ્ટુડન્ટને ખૂબ મજા આવી હશે. હજી આ તો કંઈ જ નથી, હજુ ઘણું બધું આપણે જોવાના છીએ. તો સર હવે આગળ જે મેઇન રિસર્ચ હમણાં કરંટ જે થઈ રહ્યું છે, ચંદ્રયાન-2 થ્રુ આપણે કયા કયા ડેટા કલેક્ટ કરીશું એ થોડા આપણે મિત્રોને કહીએ.
Chandrayaan-1 was basically chemical mapping of moon. We
Okay.
wanted to know what are the resources. We'll see that there is a plenty of resources. And secondly, it is not so much for resource, but if you look at, if you see moon is